Today I am joined by Dr. Stephanie Noble, who is an assistant professor in the psychology department and bioengineering department at Northeastern University, and also holds a position as a research affiliate in the radiology and biomedical imaging department at the Yale School of Medicine. She completed her PhD and postdoc at Yale University. Her advisor was Todd Constable for the PhD, and she worked on her postdoc with Dustin Shinost, focusing on functional connectivity, machine learning, and precision medicine. She's published in top journals. It's a who's who. It's Nature, Neuroimage, Cerebral Cortex, Neuron, many more. And she's currently working on a tool for estimating power for fMRI analyses, which I hope we'll get to.
Yeah.
She's also worked in the private sector as a scientific officer of Go Blue Labs and consults for elite warrior identification. So quite the resume. And Stephanie, was there anything I left out? Anything you would also like to add to that?
Oh, well, that's a super kind introduction. No, I think that's all the major highlights. I might add that one of my great passions is open science and inclusive science and supporting underrepresented scientists in academia and outside academia.
Of course.
Yeah.
That's great. Well, to begin with, I'm just going to tell a story just about how we first met and how that's going to segue into the first topic of reliability that I'd like to talk about. So I think it was back in 2017 when you were doing your PhD at Yale. Was that the time? Yeah. And I was working at Haskins Laboratories just down the street, and we were writing a grant. And during budgeting process, we had maybe 5-10 minutes at the very end. We said, just slap a resting state scan on there. I know, but it was different times. But you had just come out with that cerebral cortex paper about test-retest reliability. And I thought, wow, this is really important. So we met in person, and I said, is this as bad as I think it is? He said, well, yeah, you should be more careful probably. And I brought it back to my boss, and I quote, she said, oh, that can't be right.
Yeah.
So the first question is just to give people an overview of that 2017 cerebral cortex paper about reliability, what it means and why it might be useful.
Yeah, absolutely. So it was a little bit of a surprise to us as well. We had seen some reports saying that test-retest reliability is fairly stable, that we can get pretty precise measurements. And I will say that we find that that's true in some contexts, but the overview of this paper is that we were exploring how we can measure test-retest reliability formally measured by the interclass correlation coefficient. There are a couple different ways of measuring it at the individual edge level. And we found that reliability was around ICC of 0.2, which is below this threshold for fair reliability that's at 0.4. These are all rules of thumb, but this is somewhat suggestive that measurements are somewhat unstable relative to how great differences are between people. And we're specifically talking about, stability within person compared to between people. And you want people to look very different from one another. You don't want every time you measure a single person for that person to essentially look like a different person. So that's kind of the heart of a lot of formal measures of test-retest reliability. But we found that reliability was quite low at the individual edge level. But there are also a number of factors that influence reliability. If you look at whole brain measures or wider spread measures, you tend to see higher reliability. There are a number of processing choices that influence this. But yeah, I would say overall, we find that, really short scan durations, edge level analyses, which are very common, we tend to see quite low reliability.
You also found some differences spatially, right? So certain brain regions tend to have different levels of reliability.
Yeah, absolutely. So subcortical structures and to an extent, cerebellar structures can have less reliability than sort of the cortical structures. And if you group things also within widespread networks, we find certain networks are more reliable than others. There are a few reasons why we might see this. Subcortical structures, they tend to be much smaller. So you might have difficulty getting a strong signal from a single small structure where there's a lot of bleed over. And subcortical structures also tend to be adjacent to areas, non-gray matter areas like CSF, which have really high um, signals relative to the gray matter itself. Actually, it's a project that a PhD student of mine, Alex Fishbach, is working on right now, trying to disentangle subcortical CSF from subcortical signal in these structures. Um, yeah, so I would say that there's a lot of variability depending on what you're looking at, where you're looking at, and it's a very complex issue of what the nature of the artifact is surrounding these different structures.
I also noticed in that same paper, you showed how multiple sessions can increase reliability at a faster rate than simply scanning for more time.
Yeah.
Now, and that makes sense to me. Just practically speaking, when I told the story about how we just kind of squeezed in a little bit of functional connectivity at the very end, for people who are in that situation, they're trying to budget, they're trying to think about, what can they afford as far as scanning and how long. Obviously, it depends a lot on their question, but what would you advise them? Should they just not even attempt it if it's only going to be 5 minutes? What would you say to them?
Yeah, I think that's a really great question because we're all in this situation where fMRI, MR scans in general are very expensive to acquire, but especially functional imaging scans that can be quite long. And it's very hard to bring people back also on repeated sessions. If your goal is to do, a univariate analysis where your object of measurement is really just individual edges, um, that is one way of maximizing reliability. We also see that multivariate measures can improve both reliability and they tend to be more detectable. So we tend to have more power to detect wider scale, like network level or multivariate measures. So another way to ensure that you have a more stable measure that you're trying to detect is to consider using some wider scale or multivariate measures. And then we see something like fingerprinting. You could have very high accuracy using, so just to back up for a sec, for fingerprinting, you might use the whole connectome, or it could be generalized to other types of maps, but you use that whole connectome and you look at maximum correlation with other connectomes. And there's some similarity in that you're trying to see the highest you're trying to see whether you can detect the same connectome from the same person compared to a whole pool of other people. So this is related to that problem of, within subject variability compared to between subject variability. But we can see that you can have very high identification rates with something like fingerprinting, even with 5 minutes of data. Of course, we're using the whole connectome. We're not using, in an individual edge at a time, which is what we're measuring when we measure something like the ICC. And there are other measures like discriminability that are thought of as more formal measures, test retest reliability, that also kind of show higher rates of reliability if you're willing to take a more wide scale view.
You bring up a lot of important topics. First of all, there's multivariate, also just about including more of the brain data that's collected. I want to start a little bit with multivariate, if you could unpack what that means, because a lot of people who are just, say, newcomers to functional connectivity, they're used to doing correlation analyses. They're used to doing some kind of maybe cluster-based statistic on those. For those who are trying to learn more about these multivariate approaches you're talking about, what would be a good starting point for them?
That's a very good question, especially since there aren't a lot of widely used multivariate inferential statistical approaches that are currently popular in the field. I would say that where we do see popular kind of multivariate approaches is more in the machine learning realm. But I think that there are some interesting approaches that have been developed in the field. I'd say so. Going backwards to provide more context, as you had mentioned, some of the most common methods that people use are cluster-based inference methods. So we know that if you did a mass univariate test across all voxels in the brain, let's say 100,000 voxels or 40,000 edges, and you did just, Bonferroni correction, or maybe even an FDR correction, at least for the Bonferroni method, it's well known that that tends to have very poor power, be very over conservative relative to the number of effects that you should be able to detect. Um, so for that, we end up having alternate approaches that have been developed in this field, like cluster-based inference, that takes advantage of the fact that there is some dependence in either the connectome. So network-based statistic was developed for the connectome, or amongst voxels in a neighborhood. So that's the cluster-based inference, which was developed first. So we know that that improves power over, let's say, a very strict multiple testing correction at a pure univariate level. But you end up still limited in the fact that you can only consider voxels that are in your immediate neighborhood that are above a certain threshold. So you'll group together like a whole cluster of voxels that are all next to each other above a threshold. Same for the network-based context. You'll group together a group of edges that are all somehow connected to each other by a node that share common nodes above a certain threshold. We have found that you tend to see these islands of activation, very small islands of activation at standard sample sizes. So let's say 20 subjects or 40 subjects, when you do cluster-based inference, compared to when you use a very large sample size, where we actually see that effects tend to be widespread and distributed across the brain. So this is sort of setting the stage for why we might be interested in wider scale or multivariate approaches. You tend to see, if you try cluster-based inference in one of these in one of these large N contexts, you might get two clusters, and it's purely dependent on where you set that threshold. If it's at 0, you would get one positive. Well, you wouldn't set a threshold at 0, but if it's at, let's say zero point 0.2, a small effect size, you'd get one positive cluster, and then you'd set a negative zero point 0.2 threshold and one negative cluster that just spans across basically the whole brain. And then we know that there's also anti-correlation. So maybe this positive cluster and the negative cluster are also associated. We see a lot of evidence across both activation contexts and also functional connectivity that you can group together voxels in these large scale networks, or group together edges also in very similar large scale networks. So there are a few things that you can do. You can either move to a larger scale of pooling, which relates to a procedure that I've introduced called the constrained network-based statistic. Basically, you start with an a priori partition of a graph, though this could also be translated to the voxel-based context, where you know that these edges tend to have shown dependence within that network. So you might use a different data set to develop this partition of the network, just a way of breaking up the network into groups. And then you do the pooling at the level of these groups rather than at the level of clusters. This lets you pool together things that might be really far apart in space, but are still known to be dependent, are still known to show similar activity. So that's kind of one approach. You could move towards wider scale pooling. You can take advantage of known dependence between structures and say, okay, we're going to consider these things similar in a sense. Or you can move to some other multivariate approaches. So very common types of multivariate approaches would be something like canonical correlation analysis, or the very simplest multivariate extension of a t-test, the Hotelling t-test. And you're basically taking into consideration the covariance across every voxel or every edge together, and using that to help inform what a large effect might look like in some multivariate space. So I feel like that's trying to understand those two approaches, canonical correlation, Hotelling t-test, as extensions of correlation and t-test, are probably a good place to start if you are interested in truly a whole brain multivariate approach. Or you can do kind of a simpler approach, pooling. You're just assuming that everything acts kind of similarly within the pooled group.
That's good to know. So I use the Con Toolbox,
Yeah.
and I believe they have maybe some of those options. Again, I haven't really used multivariate, which is why I was asking the question. It wasn't just for newcomers, it's also for me.
Yeah.
And just kind of a side question is, What kind of software do you use for your analyses?
Yeah, so I actually grew up in a couple labs in my PhD lab and postdoc labs that had developed an in-house software, Bioimage Suite, um, that also relied. Some of our methods relied on AFNI, some of them on FSL. So I've used mainly Bioimage Suite for a lot of the analyses that I've done historically. I'll say more recently, maybe within the past 4 years or so, actually a bit longer. A lot of my focus has been on statistical method development after the subject level analysis stage. So at that point, I'm using something like combination of MATLAB and R, and sometimes Python to do some sort of custom analyses. Uh, so that's kind of what we're doing mainly in the lab these days. I will give a shout out again, Bioimage Suite, really great stuff developed by Dustin Chinos, Senios Papadimitrios, Todd Constable at Yale. And it's now been translated to a web-based app where you can kind of point and click and do things like nonlinear registration on the web. Actually, all the processing happens locally on your computer, but you don't have to install anything or download anything. I think that's a really cool future direction as well. But yeah, it's been a lot of different things, but these days mainly Python, MATLAB are for custom stuff.
That's excellent. Good to know. And I'm also encouraged to hear about Bioimage Suite being a web app because I
Yeah.
do see that a lot these days. And I've been using Neurodesk, which is relatively new, which is kind of a suite of many different neuroimaging tools. So I'll need to check out Bioimage Suite as well. Fantastic. So just go along with the history of what you've seen since your career in neuroimaging began. I think it was the mid 1990s that brought Biswall detects the first functional connectivity maps, and then for the next 20 years or so, it seems like a lot of people are still collecting 5-10 minute scans. Now, in your experience, you're much more involved in this particular field than I am. Uh, how do you see that changing since you published your papers back in 2017 looking at reliability? Do you think people are becoming more careful about it? What's your sense when you review papers or see talks at conferences?
Yeah, that's another super interesting question. I have seen people care a lot more about collecting longer scans and potentially, like you were mentioning before, multiple sessions of data. Um, or I think as I was mentioning before, I think another really promising avenue is using statistical methods that might enable them to be better powered to detect wider scale effects if they exist. But yeah, I think that both a whole host of work from the reliability literature. And I've certainly seen this, I think, starting in part after some of our work that suggested things may not be as reliable as they once were supposed to be, um, has pushed people in the direction of maybe we should be collecting more data. We still don't have a good idea of how much data is enough. Um, so there's a big, people might come up with this question like, how much data should I collect? And we can give you a ballpark of how much data you might need, when you have multiple sessions to get reliability at the individual edge level. That might not always have direct implications for someone's work if they're not doing like edge level analysis. They often are. Um, but you do see people asking this question a lot more and being questioned on grants a lot more about exactly how much data they're collecting. But I think part of it comes from kind of the test reliability stuff saying we're not getting very reliable measures, especially with these small amounts of data and with certain methods and other factors as well. And I think it also comes from the direction of people being more interested in within subject dynamics. So there's more interest in the idea that, to accurately estimate, let's say, states within subjects or individual subject dynamic phenomena, you also need more data to be able to fully capture and have accurate estimates of some of these things. Um, and then maybe a third piece is that people are interested in more precision medicine types of analyses. So they're interested in more deep data rather than group level data, and it sort of intersects with this idea that we have a lot of noisy data at the individual level. If we collect more individual level data, maybe we'll be able to estimate some of that noise and also have a better estimate of the signal. Yeah, I see these things moving in a positive direction. Unfortunately, there aren't clear answers to the question of how much data should I collect, and then also the question of how much data should I collect for a certain type of analysis, like statistical analysis that I would do subsequently. Um, but we're working on some things like that that might help address some of those questions, hopefully.
I'll be looking forward to it. Yeah, it's a very fast moving field. I mean, all of neuroimaging is, but especially with functional connectivity, I feel like
Yeah,
this is my impression. I think for a long time throughout its history, it was kind of seen as, oh, it's so easy to do. And so
yeah,
why not just tack it on at the very end? The person can take a nap. But my sense was, well, you spend all this time and resources and thought into designing like a really good task experiment with 45 minutes to an hour of high quality data, a lot of trials, and you're expecting to get the same amount of power or the same amount of insight into a 5 minute scan. You're not really respecting it, you know?
yeah. I completely agree, and I respect it. On the one hand, like I get it, is new stuff. We're finding some evidence of reproducible networks. You tend to observe something that looks like a default mode network every time you set a seed in the default mode. But on the other hand, yeah, people are going through a whole host of different cognitive states. We see reliability is really different when people's eyes are open versus closed. We know that there are different neural phenomena happening as well. Um, so it's very hard to think that in 5 minutes you're going to get a perfect snapshot of all of someone's intrinsic architecture.
That's true. One more question about just the technicalities of resting state scans. This is a somewhat loaded topic. I'm not expecting an easy answer by any means.
Yeah.
But for high moving populations, for people scanning children, the elderly, patient populations, people who just move around a lot in general, motion is a really big problem. And we usually, the common sense is to regress out motion regressors, see if that accounts for it. Uh, just what's your thought, your opinions about how to deal with high motion subjects that you want to keep? Some people are really invested in it. They can't afford to remove these subjects or their entire studies kaput. What would you tell them?
Yeah,
Again, not an easy question, but
but a super interesting one. I remember there was some work out recently. The authors slipping my mind. That was also showing how you see, you know, some brain activity that seems to be associated with the motion. So if you're removing motion, you could also be removing actual brain activity, which makes sense. Motor cortex is responsible for motion and other supporting structures. The whole brain, some might argue. um, yeah, I would say I think one of the best pieces of wisdom is that prevention is the best cure. Um, I'm thinking of some interesting work by Corey Horian, who's a wonderful colleague of mine, showing things for like children populations. Doing some pre-training in the mock scanner significantly reduces motion. Um, I know there are the fitted head pillows that could also be used. But when you have a lot of motion in the data, again, I think it's one of those many wonderful open questions that are predominant through this field of we don't know an exact threshold, we don't know a great choice of how to regress out motion, how many parameters to use. Um, I think it wouldn't be necessarily as problematic to, keep that data and do kind of your best to clean the data as much as possible, given that we don't have strong standards on what is absolutely the best practice. Trying to use some of the best practices that have been put out there to analyze the data, I think is helpful. But I do feel like there's something else that I'd love to talk about at some point, but we tend to throw away a lot of very useful data. Um, and you could, downweight that data. You could take into consideration the fact that you have added uncertainty in that data, but still keep that data. Um, so I would say I'm kind of on the side of it's very important to be very realistic about the fact that some finding could be due to motion if you kept that data in if you kept like a high motion subject in there. But it doesn't hurt to explore like what the effect would be of including that subject and not including that subject, being upfront about the fact that you did several different types of analyses, not hiding anything, but saying, this is what results look like when we include all data and we don't exclude things, or we're like more light on processing and artifact regression.
Thanks for your input into that. Obviously, it's, again, very difficult, and my heart goes out to those labs who really have to deal with those issues.
Mm.
Yeah, I'm totally on board as far as training, as far as piloting outside the scanner, and just making sure all your ducks are in a row before doing that. But it seems like there really is no easy answer. There's no way to completely get around it. I mean, kids are always going to move more than other people. Motion's always going to be more problematic in general with resting state than task. So yeah, we'll see. We'll see how the field develops.
Yeah, certain populations, like you just can't circumvent that very well. We can't just, not do research in those populations. At the same time, yeah, we want to balance with best practices and try doing the most rigorous state of the art things, and then also see what happens if you try some other things as a second stage exploratory analysis.
Yeah, I'm interested to see where that will go.
Yeah.
Now, on that same topic of populations outside the norm, I'd just like to get some of your overview about functional connectivity being used in clinical context, some of the interesting results that have come out over the past decade or so. I'm thinking specifically about things like there was the Stanford neuromodulation study, which was a combination of functional connectivity and then using those maps to identify regions to then stimulate to try and alleviate depression. But just in general, what are some examples of how functional connectivity has led to insight about differences in clinical populations, in diagnoses, maybe? What are some things that people should be aware of?
Yeah, I think there has been more and more research showing associations and ability to predict certain clinically related phenomena. Um, and I've been part of some really interesting studies as well, led by Rong Tao Jing, looking at using the UK Biobank data, which is, our biggest data set that has imaging and all these amazing health measures, being able to do, show some associations with various types of health measures, various types of mental health measures, and importantly, interactions between all these things and looking at what mediates what. Um, so I think that there's been some really interesting stuff out there that's quite promising. I will say I think that there's room for improvement. We tend to see that predictions tend to be quite low, or associations tend to be quite small. And I think that this is true from the effect size project that we're leading in this lab. We see that psychological phenomena, associations between the brain and psychological phenomena, tend to be quite small. Um, and I think that that's just a fact that we tend to use like these mass univariate approaches or univariate approaches. We tend not to maybe fully capture all the relevant information that's out there. So I'd say there's kind of a big host of literature out there that's saying functional connectivity might have some associations with some clinically relevant phenomena, but these tend to be quite small. And there's a lot of promise for leveraging other types of larger data sets, and more of the data that we tend to throw away, and maybe increasing these predictions, multivariate methods as well.
That brings to mind, Scott Merrick was the lead author on the paper a couple years ago, looking at, and I think it also maybe used UK Biobank, one of the large open access, not open access, but one of the large data sets looking at how much variance in certain phenotypes like psychopathology, cognitive ability, can you explain by functional connectivity and also structural methods. And I think they found that if you combine more modalities, you can explain more of the variance, but it's still pretty low
Yeah.
overall. And the key point was, one of their key points was, if you just took a random 25 subject subsample, you could get opposite effects for certain correlations, which really kind of is sobering for people who are trying to do those kinds of analyses with smaller samples.
Yeah, yeah, absolutely. And that also, makes me think of the NARP study where not just so the Merrick interval Clemens study, they're looking at subsamples of the same data set using the same processing methods. And then, then we talk about the whole multiverse of different types of processing pipelines that are out there. And you see people analyzing the same data set and getting opposite results in some cases. Yeah, I think that there's a lot of variability from all these different directions from the perspective of the processing choices, and then of course from subject level variation. And relative to this, effect sizes are known to be quite small. You can have larger multivariate effects, but our effects are really quite small. um, so yeah, I mean, I feel like it's not just unique to clinical outcomes of interest, a lot of psychological phenomena, especially things when we think of like cognitive phenomena or like fluid intelligence. That's something we tend to use a lot as a benchmark for prediction. But some of these things are also, they're very complex phenomena. They're multifactorial. They can be context dependent. Theoretically, some of them shouldn't be, but still, um, I feel like there's a lot of room to sort of come back to the basics and sort of really appreciate the fact that these are very small effects. Think about ways that we could use some of this data in combination with other types of data, ways that we can bring back some of the data that we throw away to help improve some of our inferences. Um, and also at the same time being very rigorous about the fact that what if these results are due to some other secondary phenomena or artifact or confound. We should include all the data, but also be very aware about parsing apart what are the actual influences, what are the actual uh, underlying phenomena that are responsible for the predictions and associations that we make.
Definitely. And I'm very curious to see how, as we move forward, I thought in response to that Merrick paper, Katerina Grattan wrote a very insightful commentary about the differences between these smaller studies, what they're able to do, and what we can do with these much larger databases. So, for as far as a cross-sectional, correlations between, you know, behavioral effects and brain data, it's not looking very good for the traditional 20 to 25 person sample. So we may need to rethink going forward exactly what we're going to use functional data for in smaller studies.
Yeah, yeah, absolutely. I'll add also that uh, part of our effect size explorer is really trying to tease apart what exactly are our best estimates of effect sizes and most conservative estimates of effect sizes across a range of many different typical kinds of fMRI studies. And there are some study types, like if you got really lucky to look at certain brain areas, like you a priori happen to know which brain areas were uh, showed the largest effects, maybe because of prior studies, and you were doing some within subject analyses, like within subject task-based activation. You might need substantially fewer subjects to detect those effects. You might have much larger effects in some of these cases than in others. But the reality is, many of our studies involve very complex cognitive phenomena, and also might involve mass univariate studies. So you have to protect against false positives if you're just doing kind of a blind search across the whole map, and you lose power from both of these things. But hopefully we can start to work together as a field to have a better sense of what these effects look like so we can plan accordingly.
Well, let's stay with that topic of power and also effect sizes, because I want to get into some of these toolboxes that you mentioned about effect sizes and power. I don't want to just restrict you to functional connectivity. Your range is greater than that. So, if you could tell us a little bit about these projects and when they might be available, or can we use them right now?
You can use them right now. They're
Oh,
yeah,
okay.
yeah, yeah. I
That was
we
not a
haven't.
softball. I didn't set that up. I'm curious.
Yeah. No, I love it. I love it. It's great timing because we're finalizing. Hallie has a draft, and we're Hallie Shearer is my extremely talented RA who's been working on the Shiny Explorer for the effect size Explorer, and a lot of the processing that we're doing to sort of convert everything to appropriate effect sizes and be really intentional about what sorts of effects that we present. But yeah, we have a Shiny app that's available. If you go to the lab website, it's I think neuroprismlab.github.io, something like that. And then you go to the tools section. We have the effect size explorer there. Um, it is we call this kind of our beta version. It's it has a full map of certain of effect sizes that you can already get a sense of. If you need a ballpark estimate of, if I'm doing a task base, I'm doing like the HCP emotion task, what sort of effect sizes might I expect? And we can show you what sort of effects we have tended to record there. But we're also revamping this with a number of different types of effect estimates, multivariate effect estimates, network-based effect estimates, and a few other types of things that should help people with understanding what the spatial distribution of effects might look like and mapping them between different types of atlases. So that's available, and hopefully in the coming months we will have some more user focused kind of technical um, manuscript out about that. And then we'll have a different manuscript that explores really the types of effects that we have and their implications for the field. But sort of more user guide type of almost documentation like manuscript will be coming out soon, I hope to, and the latest version of the app.
Excellent. And does that include the power estimates as well?
So for this first step, it's just the effect size estimation. Um, so we have something like um, six different data sets, including UK Biobank, ABCD, HCP, and a few others. And then we have task-based activation, functional connectivity, a number of different phenomena that we might predict, clinical variables, cognitive variables, biometric data, all sorts of stuff. So just sort of the first step to making a power calculator is to first estimate all these effects across all these different contexts and sort of translate them into effect sizes that might be relevant to the community. And I think that that in itself is helpful. Like if anyone was to do a standard power calculation, they need an effect size estimation. So they could take some of these effect maps and then plug them into, G power or R's power function. But then, so that's stage one, and that's almost done. The next stage will be developing a power calculator for this. Now that we've laid the framework, we have some Shiny infrastructure, we have the effect maps, we have sort of a pipeline to start analyzing stuff. That that's kind of all set up for that next stage of the power calculator.
That's great. I think that'll be so useful because I remember this was maybe about a decade ago. Jeanette Mumford had made an fMRI power tool in
Yeah.
MATLAB, but it was no longer supported after a few years. And then Yoka Durnas made a web-based power calculator, which I also thought was really useful. But then I don't think it's supported anymore. So anything in that regard would be very useful for people designing their experiments.
Yeah, yeah, I think so too. And those are phenomenal resources that were out there and unfortunately are no longer available. Besides that, the standard power calculations, they serve univariate analyses or some mass univariate analyses with multiple testing correction. But as you know, we have very idiosyncratic inferential procedures in this field, like cluster-based inference. So and some of those procedures that you mentioned, they rely on, parametric cluster-based inference, so random field theory-based estimates of, error rates that we might get using random field theory for cluster-based inference. But there's some work out there, some work that I'm a big fan of by Anders Eklund that talked about how it's well known that certain assumptions can be commonly violated, but it's sort of showing empirically how problematic some of these assumptions are or the violation of these assumptions are in practice. And then pointing towards the idea that we might want to use some non-parametric procedures instead that tend to control error rates at expected levels. I would say that we don't currently have procedures out there to estimate error rates for non-parametric procedures. They are by nature non-parametric, but we've developed some procedures. If you're curious, you can read about them in our cluster failure or power failure paper, or in our uh, leveling up paper that talks about how you might use some resampling of large publicly available data sets to estimate power. And that's the procedures that we'll be using for this. So this enables us to not just use parametric procedures, for which there may be closed form solutions for error rates and estimates of power, but any kind of arbitrarily complex inferential procedure that someone might develop for the field, we can, try to make our best empirical estimates of power for that. So I think that's something nice about this. That might be an addition over the really on top of the really great foundation that's been built by other power fMRI specific power calculators, is both the ability to estimate power for arbitrarily complex inferential procedures and also using real fMRI data and the complex spatial structure of that data.
I'm looking forward to that. That's great. Yeah, so I'll be on the lookout for when the papers are published, detailing how to use them. But yeah, the Shiny app is already live. Yeah, I'll give it a
Yeah.
spin and see what's up.
Please do let us know how you like it.
Yeah, well, yeah. Great. Well, I know that you're also working on many different projects at this time. And one concept you've been developing, I've noticed in some of your recent papers, is talking about localizationism and anti-localizationism. So this is more conceptual, but it ties into a lot of what you're talking about as far as, say, multivariate approaches, using more of the brain, more of the voxels to try to understand the functional architecture of what's going on. So this was a paper that came out, I believe, this year about anti-localizationism. And I thought it was, again, very interesting because this does seem to be a trend. Whereas, historically, I think we kind of started at the voxel-wise, family-wise error correction, then we kind of moved to clusters because we know that there's spatial dependencies between neighbors. And now we're moving towards an even kind of larger scale view because we know the brain is very complex, in some senses, irreducible organ. So if you could elaborate a little bit about that current line of thinking you're working on.
Yeah, I love that you bring this up because a few reasons. One is that some of the more recent conversations about localizationism and anti-localizationism, often in kind of other words. There was a very important paper by Lisa Feldman Barrett, and then a counterpoint by Nancy Kamwisher, where I think that there was a lot of conversation about, oh yes, of course things are distributed, or of course there's localization, as of course, like, there are focal processes at work in the brain. Or then, other people saying, why are we even having this conversation? It's obvious what the answer is. And then, but it's not obvious because there are people who are saying very strongly on one side or very strongly on the other side, their opinions. Um, I would say that we wrote this paper about anti-localizationism. Joshua Curtis and I have had a lot of conversations about this, and then Dustin Chinos and Luis Pessoa, we started having conversations with them too, and we're just really excited to put forth our thoughts about this. And I would say that anti-localizationism is just this idea that there are things that are more than just focal processes and that they're not just focal processes. So you could have processes that are maybe exhibit with some level of statistical regularity more, let's say, activity in certain areas, but just this idea that that's not all. And I would say, some people are thinking that this is kind of trivial. Of course, we know things are distributed, blah blah blah. But just like you brought up, the field comes from a history where, for a number of reasons, especially for reasons of computational complexity, we have really large data sets, and it's not trivial to run even simple mass univariate analyses on them. For reasons like this, we have, very popular methods that are operating more so at the univariate level and subserve our ability to make very focal inferences. So if you've used for decades, cluster-based inference, you might explore a certain phenomena, a certain cognitive phenomena, and say, oh yes, we've seen all the history of the literature says that this cognitive phenomena is associated with activity in this one area. This one area. We see it again and again. And then you have this, self-fulfilling cycle where people end up doing more research, looking specifically at that area, and they use the methods that are designed for localizationism. So I think even if, some people have it in the back of their mind, oh yes, the brain is distributed, everything is, everything's connected, blah, blah, blah. In practice, you have this historical reliance on these methods that have enforced a very localizationist view of how the brain actually operates. So I think it's very much not a trivial question, and there's still a lot of debate about this. And it's the most non-trivial part is that we have all this knowledge that's based on these localizing methods.
Mm-hmm. Yeah, the history is really important to understand because that does bring us to where we are today and where we're trying to develop and grow from. I do know that, as technology advances, obviously the multivariate and even multimodal approaches can become more feasible. But I'm also noticing that as we get stronger scanner technology, we can do layer specific imaging. That can be really useful for things like primary motor cortex and somatosensory cortex. But I think for some of the more higher level abstract phenomena people are talking about, it's going to be necessary to be more familiar with these more whole brain integrated approaches.
Yeah, yeah, I agree. And I'd say both are very important. We know that we tend to see with some level of regularity that some more focal circuits sometimes are or tend to be associated with certain types of cognitive processes. But even people who study phenomena that we would expect to be very focal often say, this is still just a piece of an embedded system. You can sometimes see, lesions to certain parts of the system and shifts in which part of the brain circuitry supports that functions. So I think that this is all kind of evidence that there's multiple realizability. There's things that can be instantiated in many different ways in the brain, which means that there's not just one single unique, system that subserves a certain function. Um, but especially like you're saying for more complex cognitive phenomena and things like psychiatric disease that we know is extremely complex. I think that it's even more so immediately apparent how helpful some of these other approaches that take advantage of the distributed and connected nature of the brain could be.
Yeah, I agree. Now, I want to end with a couple, again, kind of higher level questions.
Mm.
And these are, it's for the general audience, but also maybe targeted more towards newcomers. Uh, we touched a little bit on this, but for somebody who is just dipping their toes into functional connectivity analysis, it can seem very overwhelming at first because they may say, well, I kind of have this idea. I'm just trying to see correlations that maybe give some insight into connectivity, so to speak. What would you, again, recommend to them? I'm putting you on the spot a lot with these, but for somebody who's just coming into it, should they get acquainted with these multivariate, more advanced techniques before they attempt their own experiment, or what would you recommend? And I know you have graduate students now, so how are you I guess another way is to say, like, how are you training your graduate students in these methods?
Yeah, that's a lovely question. And I actually I wouldn't recommend that people jump right into learning about multivariate methods or more complex methods right off the bat without getting an intuition for some of the stuff that these things build off of. Um, so actually, there are a few stages of this. There's kind of, how would you analyze the data? And then how would you do sort of, or how would you process the data? How would you do statistical analysis? And there are levels of statistical analysis too. So um, for the kind of processing side, I would recommend like complete newcomers visit some of our kind of best state of the art, best practice kinds of tools for doing processing and analysis. So things like fmyprep, I would start there. I would try to read the paper, the core fmyprep paper that talks about why they made decisions that they made. Maybe then go on to, Jonathan Power's reading list, where he talks about a number of important early discussions that were being had in the field about things like motion artifact and GSR and stuff like that. Um, and how sometimes we try to account for these things, but we really can't fully account for them. And then, things like Khan, I think the Khan toolbox is also very helpful. And I trust Sue Whitfield Gabrielli. She's a colleague and a wonderful person. I think that there's tests that's also based in my own experience. I think that they've laid out very carefully their reasons for making certain decisions in con, and you can sort of follow their paper as well. Um, so that's on the processing side. Then we get towards analysis, and I'm going to skip some of the subject level, first level, second level analysis, but sort of talk more holistically about what sorts of group level analyses we would want to do. That's where you can move to a multivariate analysis, but I think it's a little quick. The way I teach it, I have a class that I've created last year, which is a data science toolkit for human neuroscience research. So very excited to teach this class and create this class. I actually have been thinking about this for years. It's cross-listed in psychology and bioengineering because I come from these two backgrounds. Um, just a quick aside, so I had my undergraduate training in chemical and biological engineering at Princeton, and then I was in interdepartmental neuroscience program for my PhD. And Todd is in biomedical engineering, and his lab is full of engineers and neuroscientists and people who are getting their MDs and PhDs and lots of stuff. And this is very similar for Dustin's lab as well. So I feel like I've talked a lot with people across the spectrum of engineering, psychology, statistics. And statistics is the direction I've gone in a little bit more, MR statistics. And I feel like uh, it's very helpful for everybody to get a good sense of just the basics of linear modeling. Like, can you run, not just can you run, but can you understand the machinations of a simple regression? Can you fit a line and see what the residuals look like? And then once you get an intuition for that, you can build up intuitions for, multiple regression. And then you can see how things like just a really simple linear model and how we think about errors on a simple linear model can generalize to things like multivariate linear models, or things like machine learning, deep learning, bunch of logistic regression models kind of attached to each other. There are a lot of mass univariate filters in our field, things like CPM. Also thinking the HCP Megatraw. They're both, you're basically doing mass univariate models and applying a filter, and then summarizing your leftover results. But like these are all based on getting a really good intuition for a simple linear model and how we use that to estimate errors. And that's something I try to really hammer home across, in the class and in the lab.
That's a great answer. Yeah, and I'm in complete agreement about focusing on basics first before jumping into the more abstract stuff. It calls to mind, I once knew this professional cellist who had phenomenal technique. And one of his favorite things to say was, basics doesn't mean that they're easy. It means that they're basic. Like, you need to know these before you go on and do everything else. So I think that's a great approach. And I think that's great advice for newcomers and everybody else, really.
Yeah. Yeah. I feel that way too. I think that there's a lot of return to basics. And if I could add really quickly, I think that this is a major trend in the field. I think that there's a lot of excitement about just coming back to basics, basics of what is a p-value and should we be thinking about certain types of thresholds? Should we be doing standard frequentist inference? What sort of effect sizes we might expect? That's, Jacob Cohen wrote his influential textbook in 1988. It is still fairly, I guess, recent relative to the whole career of psychology as a field. Um, but these are really basic ideas, like just having a sense of what effect size you're measuring. It's really fundamental for us to make all kinds of inferences. I feel like we've talked about one trend, which is, getting more information, subject level inference, multivariate information, time series stuff. We tend to condense that into like measures of mean and variance, or related measures. But then this other trend, I think, is just this idea that people are interested in returning to the basics. Are we measuring things properly? And that really underlies our ability to make strong, robust inferences.
Yeah, I think it'll be great for the field. I'm appreciative of all the people who are really putting in the work and putting out some of these theory and kind of proof of concept papers about why we need to rethink some of what we've kind of taken for granted as a field.
Absolutely.
Well, on that note, I think this was very illuminating. I'm very excited about what you and your lab are working on, and you and your colleagues. And I hope that maybe a year, 2 years from now, we can touch base again, see how the field has changed, see if our predictions are right, just see what's going on.
I would love that. And thank you so much for having me. As I mentioned before, the lab is absolutely thrilled that I'm here. I'm thrilled to be here. Shout out to Hallie and Alex, who are my phenomenal lab, and then newcomers, Fatima and Fabricio recently. So thank you so much, Andy, for having me. This has been really exciting.
Of course. Thanks for your time.